Okay, welcome from my garage here. We're going to continue chapter 16, solutions. And so solutions are homogeneous mixtures, and we're primarily going to focus on liquid solutions. And within liquid solutions, aqueous solutions that are solutions with water. And so let's take a look at where we were talking earlier. The solutions are going to be the mixtures, and oftentimes the mixture is going to have a minor component that is a small amount, which would be the solute, and a major component, which is the solvent. And for aqueous solutions, the solvent is water. And so this is a little bit of a review of what we were talking about earlier. And so here's a copper 2 sulfate solution. This copper 2 sulfate, which is a solid solute, but sulfates are soluble except for silver, lead, mercury, calcium, strontium, barium ions. And so we can dissolve some of this in here. However, it's not infinitely soluble. There is a solubility limit, which we call the solubility. There's two definitions for solubility. But here we dissolve these and we create aqueous copper 2 sulfate. Copper 2 sulfate is a soluble salt, therefore it's a strong electrolyte, and so the ions break apart. So the copper 2 ions, which are these small ones here, are going to be surrounded by waters. The oxygen end of the water is going to point towards it because those are the negative ends of water. And that's going to help stabilize the ion, that is the charge there. And so these structures here are called hydrated ions or solvated. Solvated if it's a different solvent than water. If it's water, it's hydrated ion. And these waters aren't permanently attached here. There's exchange, so another water can come in and melt this water off. Sometimes they are bonded to the ions, but you'll learn more about that in Chem 1B. Here we have the hydrated sulfates. Now, the sulfates are going to be spherical in nature. Or this is not copper 2 This is not copper 2 sulfate. This is copper 2 chloride. Although it looks like it. And so these would be the chloride ions over here. These are going to be hydrated with the opposite end of the water. The hydrogen end of water is positive, the negative end is the oxygen here. And so we have hydrated chloride ions and hydrated copper 2 ions, and that helps stabilize the solution. And this is soluble, not infinitely soluble, but soluble. And we can add concentrated solutions and dilute solutions, and so the color is going to vary. And so you can see the difference in colors. For example, here would be a more dilute copper 2, which gives a light blue color. Here's a more concentrated copper 2. Just looking at the solution, ignore the crystals. These are crystals of what appears to be copper metal. Or no, these are silver crystals, sorry, forming on copper wire. This is a single replacement reaction here, in which the copper metal, which is this piece of wire here, is being attacked by silver ions. And we'll need this is silver nitrate, so we'll take 2 silver nitrates. And that's going to form copper 2 nitrate. Nitrate salts are soluble, so it's aqueous. This should just emphasize it. These are aqueous solutions here, plus silver metal. And the silver metal, initially when it precipitates here, it forms a black coating. As the crystals grow larger and larger, then you can see the silver, the lustrous silver color of silver metal here. And that's precipitating on the surface of the copper. The copper is being eaten away, and so it's forming the copper 2 solution, which is this blue color due to the copper 2s. Nitrates are colorless, so you don't see that. And so here's an example of dilute and concentrated. However, we can't have infinitely concentrated because there is something called the solubility limit. And the solubility limit here, it's all relative to the solubility limit, how concentrated we can get or how dilute the solution is. And so the solubility in quantitative terms is a measure of how much solute will dissolve, and in a given amount of solvent at a given temperature. That's the quantitative definition of solubility. There's also a qualitative definition. And so solubility is the max that will dissolve. And so that's this definition here. But we also have the qualitative definition. Qualitative definition of solubility is it's soluble. Um, Qualitative is does more than 0.1 moles dissolve per liter of solution. And so it's greater than 0.1 moles. Then we have insoluble, which is qualitatively, less than 0.1 moles of solute. So, for example, copper 2 chloride, more than 0.1 moles will dissolve in the liter of that solution, and therefore we call copper 2 chloride soluble, not insoluble. And so this is moles of solute per liter of solution here. And then slightly soluble, is at the border. It's not black and white, and so we have a little border here, which we'll call slightly soluble, in which about 0.1 moles of solute dissolves in a liter of solution here. And so the max here we look up in a book or a table, and look, Wikipedia is pretty good for this, but this is free, of course. Well, unless you donate or whatever. Then we have Wikipedia about their paid sources, and so CRC has a good amount of data for this. And so this is the CRC. CRC stands for Chemical and Rubber Company Handbook, etc. Handbook of Chemistry and Physics. And this is a paid source. This is pretty good. And since it's a paid source, it's updated every year. So the data is pretty good. When we hit that maximum, we form a saturated solution. So this is at the max here. We could have an unsaturated solution, which is less than the max here. And so saturated and unsaturated. It is possible to have a supersaturated solution, in which we have greater than the max. But this is unstable. And there are different ways that we can form it. A supersaturated solution. One way we can form a supersaturated solution is for supersaturated solutions, which are more than the max. The question comes up: how do you have more than the max to go into solution? And so the way that one gets more than the max, let's see, there it goes, is to get the max in at a higher temperature. And so in this case, we increase the temperature. Normally when you increase the temperature for solid solutes, this is sodium acetate. Sodium acetate normally is soluble, but it has a limit. And that limit depends on temperature. And this one, the solubility increases dramatically with temperature. So if you do the sodium acetate in water, and then you pour way too much. This is like sugar. Sugar cubes are soluble in water, except there is a limit. And so one way you can increase that limit is warming up the water. So if we warm up the water, then we saturate this at elevated temperature. So this is going to be saturated. And then what we do is you cool it down. And so we cool it. When you cool it down, then the solubility decreases, because normally when we look at the solubility versus temperature, solubility versus temperature, we see an increase in the solubility. And so this is typical. Not everything. For gases, for example, this is for solid and liquid solutes. Solid, liquid solutes. For gases, we see the opposite because the solubility of the gases is already kind of low, and then as you increase the temperature, the solubility decreases for gases. We're going to see some solid solutes actually decrease solubility, and that's more rare. But sometimes what we'll see is a decrease for the others as well. But the most common trend is an increase in solubility with temperature. And that's what's seen for sodium acetate. So what you do is you get a saturated solution at a high temperature of sodium acetate, and then you cool it down. And what happens is nucleation of new crystals is sluggish. It depends. Nucleation, because of the acetate, the shape of the acetate ion is more complex, so it's harder to nucleate those crystals because acetate is uh, of its shape, because of its shape. And so nucleation is sluggish for sodium acetate. Other things, it isn't sluggish and immediately crystallizes out, um, but because of the structure or the shape of sodium acetate, it's a little harder to nucleate those crystals. And so this is called a seed crystal here. A seed crystal just provides a template for crystal growth. And so we're not going to nucleate naturally. We're going to nucleate, I guess, with help. And so we nucleate with help of the seed crystal. We drop the seed crystal in there, and then that provides a template. And so the acetates and the sodiums can nucleate there. But there's still a lot of sodium acetate dissolved in here because it is soluble, but they put way too much. And you can see a lot of crystallization here, so a lot came out. There's another example that I should talk about. This kind of review, and that's bubble nucleation. And this is with CO2 here. Gases, the solubility of a gas is going to be proportional to the pressure of the gas above the liquid. And so here, if we have, let's say, 1 atmosphere of pure CO2 gas, it's a lot. But in air, the pressure of the CO2 is very, very, very low. And so all of a sudden we go from 1 atmosphere of CO2 to less than it's less than 1%. So let's say about 1% of that. So 0.01 atmospheres or less than 0.01 atmospheres. And so what's happening with 1 atmosphere of CO2, it's forcing along the CO2 into the carbonated beverage here. And then when we open the lid here, what happens is CO2 escapes, air gets in, air has a much lower partial pressure, and so we get supersaturated solution with CO2. Now we have to wait for bubble nucleation. It's slow, so eventually this will go flat as the bubbles nucleate and then the bubbles release. But there are things to speed up, what we call catalysts. Catalysts to speed up the reaction. So catalysts would be like Mentos. Mentos is like the seed crystal that we saw earlier. And what happens with the Mentos is it has structural features there that promote bubbles, little baby bubbles, nucleating on the Mentos itself, the Mentos candy. And so I think I showed the video, or you can watch the video, the people dropping Mentos into Diet Coke or some other diet beverage. It works better with diet sodas, I think. And so, and then that promotes bubble nucleation, and we see the rapid geyser liquid coming out there. All right, so that's supersaturated, where we have more than the max, and then this is infinitely soluble, and so there is no max. One way of thinking about infinitely soluble is like a thought experiment. If you have water, how much water can you dissolve in water? And so if you think about water and water, there's no limit to how much water you can add to water. Well, there are some compounds that are similar to water, in a lot of ways. For example, hydrogen bonding is very important. and small size, or even larger size, but lots of hydrogen bonding. And then those are infinitely soluble and miscible. So examples of this would be methanol. Even though we have a methyl group instead of the hydrogen here, the methyl is still kind of small, and so this is very water-like. So methanol in water is miscible. And even ethanol, I mean, we have this hydrocarbon part here, CH3CH2, it's becoming less water-like, but this is still miscible. And so we can dissolve an infinite amount. And what happens is that the solvent-solute relationship flips. So when we go to more than 50% methanol, should we still call it an aqueous solution, or should we call it water dissolved in methanol? So let's say it's 90% methanol, 10% water, then that's more like water is a solute, methanol is a solvent in that particular instance. And the same thing here. However, when we go to propanol with 3 carbons here, this is becoming less water. This is more hydrocarbon or more oil-like. And so this is not miscible because of this. This is the non-polar end of water, so this is quite non-polar. This is also non-polar, but it's small enough that it doesn't create trouble. Immiscible would be like, okay, if it's all non-polar. So let's take a look at something like methane or ethane. We'll do ethane here. Ethane is immiscible. Ethane's a gas. Methane's a gas. Methane will just bubble through water. We have some liquids like hexanol. Hexanol would have 6 carbons. So that's 6 carbons here. This is a liquid. Ethane's a gas. This is a gas, and these are immiscible. Immiscible usually refers to a liquid, and miscible is often like that. And so we would say that hexane is immiscible. What happened with hexane? It would be like oil and water. It depends on which one's more dense. One will float, the other will sink. We could also have like things like chloroform, which is CHCl3, and others. This is liquid as well. And so normally we look at immiscible, and this is usually liquid and liquid. And so these would be classified as insoluble. These liquids would be classified as immiscible liquids, usually. So we can see that here. We see 2 miscible liquids. So octane and chloroform are similar. They rely on London forces primarily. And so they're similar enough that they're miscible. Miscible means that they're infinitely soluble. This is like mixing water with water. They're that close, but although these are quite different. However, gasoline, which is a mixture of hydrocarbons, long chain, short chain, and other things, and water don't mix. Water is primarily hydrogen bonding interactions. Gasoline is primarily London. And in fact, gasoline's only London. There's no polar species here in the hydrocarbons. And so that means that you have to break apart a lot of waters to fit one of these big molecules in there. It's not energetically favorable. And so, although water does have dispersion or London or instantaneous induced dipole or induced dipole, whichever of those you want to use for that. So, okay, we talked about formation of the solution. If we're looking at aqueous solutions, then water is very polar. And so the water molecule is very polar. And so water is going to dissolve polar solutes. Polar solutes could be like ionic solids, negative ions and positive ions, or it could be polar molecules, like methanol, ethanol. Those are polar molecules. And so we got that. So for formation of the solution, we talked about hydrated ions, that helps stabilize it. And so we can dissolve ionic compounds. Water is good at dissolving a lot of salts as long as the ionic bond's not too strong. But if the ionic bond gets too strong, then it's too hard for water to break it apart and dissolve it. But sodium chloride is okay. So we can take solid sodium chloride and dissolve that. And we'll look at the process, the dissolution process. But once we saturate it, we set up a situation where we have a dynamic equilibrium. So this is saturated, i.e. it has max amount of solute here. It's a state in which opposing changes happen at equal rates. We saw dynamic equilibrium happening in other things. Well, dynamic equilibrium also happens when we do saturation. So for example, here, this is unsaturated. There's less than the max. This is also unsaturated. This is less than the max. In this case, we're just dissolving in water, so there's nothing in here. But once we start having species in here, then what happens is the species can come back and, like a seed crystal, provide a template for it to attach, and so it sticks. So particles can come back and reattach, and then at the same time, particles are leaving here because of the interaction with water. Once we hit this equilibrium, that is, once we get the rate of dissolution is equal to the rate of crystallization, then this is saturated. We hit this max. And so this would be at the max solubility limit. And the max solubility limit differs depending on the solid. Some solids, very little dissolves, other solids, a lot dissolves. And so this would be a situation where we have the dissolution or the dissolving rate and the crystallization or the precipitation rate are equivalent. All right, let's take a look at the dissolution here. And so when we have dissolution here, the water molecules are breaking apart the sodium chloride lattice and forming the hydrated ions here. The hydrated ions can come back and reattach here. It depends. When we hit the saturation limit, we have to have way too much sodium chloride. And that's a lot of sodium chloride because this max solubility of sodium chloride is 36 grams per 100 milliliters. So we have to have like 37 grams that we try to dissolve. And so 1 gram remains undissolved. And so what we're going to have is we're going to have excess sodium chloride crystals there, and then we could have, crystallization or precipitation, and we could have dissolution, occur, and when those occur at the same rate, then we hit this state of equilibrium, that is, where the concentration doesn't change. However, it's dynamic because dissolution and crystallization never stop, and so that's what we get for that. All right, what are the factors that determine? Well, one of the factors is how strong the ionic bonds are. If the ionic bonds are too strong, then it's insoluble. That's one of the factors. And it also depends on how stable these hydrated ions are. But there are other factors here. The strength of the intermolecular forces within the solute. Intermolecular forces would be the ionic bonds for solid ionic solids, or it could be, there are other things. So, for example, covalent bonds. And so intermolecular forces here are not necessarily intermolecular forces. We should say bonds and intermolecular forces. Bonds and intermolecular forces. And the bonds, what types of bonds we have? We have ionic bonds, right? And we also have covalent bonds. Covalent bonds are very difficult. And we have metallic bonds. Metallic bonds, too, are as well. And so most covalently bonded substances and metallic bonds. So as far as covalent bonds go, we have things like diamond, or quartz. Quartz is SiO2, diamond, which diamond, which would just be carbon solid here. And For metallic, we would have things like gold, AU, etc. Those aren't very soluble. But some of these ionic bonds, yeah, those can be undone. Let's see. A good look at the structure. Let's take a peek at the structure of diamond. Oops, diamond. Let me correct this here. Basically, it's this. It's too hard to break apart these covalent bonds. This is kind of showing the geometry of these. These are tetrahedral, tetrahedrons, these orange things. And they're just showing the tetrahedral bonding network of the carbon atoms. All the carbon atoms are tetrahedrally bonded. So I'm just trying to show that there. But those bonds are too hard to overcome for that. And so it depends on the strength of the forces holding the solute together. We have to break, the factors that determine the solubility, we need to break the solute. Break solute. This is one factor. The next factor is we have to break apart the solvent as well in order to make room. Like, for example, if you have a big oil molecule, we need to break apart a lot of waters to fit that in there. So we have to break solvent. And another factor is we form the solute-solvent interaction. In this case, these are the hydrated species here. Hydrated ions or hydrated molecules or whatever. Hydrated species, we'll call it, because it doesn't always have to be ions. And so those are the factors here. Now, when we're looking at a gas, it's going to depend on the partial pressure of the gas. And so this is for gases here. So the example, if I had 1 atmosphere pure CO2, this is just pure CO2 that's in the headspace of the drink here, versus air, which is much less than 1 atmosphere here. And so the concentration of the gas, that is, how much gas I can get in there, is proportional to the partial pressure of that gas. And so this is the concentration of the gas in the liquid. There is a proportionality constant here called the Henry's law constant, and there's an equation that governs this called Henry's law. It's just a direct proportionality. And the temperature, the particles move more quickly. So for solid and liquid solutes, increasing temperature, solid and liquid solutes, typically increasing temperature means increasing solubility, S. However, for gases, the increasing temperature means decreasing solubility. And so the solubility should go down for gases. All right. Then we talked about intermolecular forces here, and solubility here. Ethylene glycol. Ethylene glycol is very water-like. There's 2 alcohol groups on this, and so we have an ethylene here, 2 carbons, and then 2 of these alcohols. So it's very water-like. So ethylene glycol dissolves easily in water. In fact, it's quite miscible in water. However, oil's not. And so look at that. Here's partial pressure. As the partial pressure increases, the gas, then we can force more of the gas into the liquid phase. And so solubility increases with increasing pressure here. And we can make supersaturated solutions, if bubble formation is sluggish. Bubble nucleation, we call it. When we look at temperature, most solid solutes increase in solubility, increase. However, some of them actually decrease, like lithium sulfate here, it actually decreases, and sodium chloride is about flat here. Its solubility doesn't increase. But some of these, we see a dramatic difference between the high temperature solubility and the low temperature solubility. And so these are candidates for supersaturation. We heat up sodium nitrate. It depends on how sluggish the crystals are to form, and cool it down. If nucleation of new crystals is slow, we might supersaturate it. And so here they're doing ammonium chloride is dissolved in warm water. So ammonium chloride is more soluble in warm than in cold. And then they cool it down. Here, ammonium chloride has no problem nucleating crystals. So when the ammonium chloride's cooled down here, the crystal formation is immediate. Whereas for other things, the crystal formation might not be so immediate here. It might actually take some time to happen. Pause it for a second. So you don't have to know any of these numbers, but just in general, solids and liquids, the solubility increases, gases decrease. When we're looking at the concentration, there are different units we can use. Molarity is one of them, percent by mass. We just have this percent of A is equal to, this is by mass, so it's just equal to the mass of A over the total mass times 100%. Some people like the percent. I personally, I'd like to put the units on here, percent, because, for example, if the concentration is very low, then we don't have to use percent. We could use other units. For example, part per million. So the ppma is equal to the mass of A over the total mass. But rather than multiplying it by 100, we multiply it by a million, which is 10 to the 6 ppm. So I'd like to put the units on there because sometimes we multiply it not by 100, but by million or billion. That would give us part per billion or trillion, etc. And so this is for low concentrations, and this is for higher concentrations. We use a percentage. For lower concentrations, we use ppm or ppb or ppt, part per trillion, even for extremely low concentrations. The total mass here is just going to be the mass of the solution. And the mass of the solution consists of the combined masses of the solutes. There could be more than one solute, so we just add them all up, plus the mass of the solvent. And that gives us the total mass. So this is a percent concentration by mass. One thing we often need when we're dealing with percent concentration by mass is the density, which sometimes we have, sometimes we don't. So let's take a look here. This is a straightforward problem here. 125 grams of solution, so that's the total mass. This evaporated dryness, 42.3 grams of solute. So this is just grams of solute over total grams times 100%, because it's 33.8% here. You are to prepare 2.50 times 10 squared grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? And so 250 grams of 7%. We know 7%, we convert percentage back into fractions. This would be 7.00 just by dividing by 100 rather than multiplying by 100. So we have this 7.00 grams of sodium carbonate solute over 100 grams total. And we're going to use that as a conversion factor. And so here, we can just figure out how many grams of solute we need. And then how many grams of water. That is, we take the total mass, grams of solution minus grams of solute. That's going to give us the grams of water. And so we'll have 233 grams of water using a density of 1.00 grams. Now this is the density of pure water, not the density of the solution. And since we're just asking how many milliliters of water, we can use that to give us that. Molarity is very common. This is moles per liter of solution. And so this is a very common way of expressing concentration. And so there's some molarity type problems. calculate the molarity of the solution made by dissolving 15 grams of sodium hydroxide and diluting it to 100 milliliters. In this particular case, they're telling us the volume of the solution, not the volume of water. And so it's very important here. It's volume of solution, so it's 0.100 liters. And so just take the moles divided by the liters, we get the molarity, 3.8 mole. This particular problem. Molality is moles of solute per kilogram of pure solvent, not kilogram of solution. And so that's important, not solution. Molality is important because it doesn't depend on temperature. And so this is temperature independent. That's one of the big advantages of molality. Whereas molarity, the volumes can expand or contract with temperature. And so we have to be careful. It doesn't expand and contract by much, but a little bit. And so that could lead to changes in molarity. However, molality doesn't. And so things where the temperature is changing, we would use molality instead. And so here's an example of using molality. How many grams of potassium chloride must be dissolved in 250 grams of water to make 0.400 molal? No, molality has a little m. Little m is used for so many different things, but in this case, it's molality. So we need 250 grams of water. That's pure solvent. And we need, let's see, 0.400 molal. So we can use that as a conversion factor here. That is 0.400 molal of KCl in 1 kilogram of water. And that will be our conversion factor here. So 250 grams of water, convert. I don't like this necessarily. This is a kilogram of liquid. Well, actually, I guess it's fine. So we go from grams of water to kilograms of water. Kilograms will cancel out kilograms here in molality. It gives us moles, and then goes to moles. I take that back. This is how I would have solved it here. We get 7.46 grams of KCl. Normality, we're going to skip this. This equivalence. If you're doing a lot of titrations, normality is useful, but we're not going to deal with normality at all. We're going to be dealing with percentage, maybe parts per million as well, molarity, and I might have mentioned molality. We don't do that much. There's one application, molality, which I'll talk about, and normality, not at all. So skip that entirely. There's another thing, solution dilution, that we do. Solution dilution is taking a concentrated solution and diluting it. And this is a solution dilution equation. I'd like to say M1V1 is equal to M2V2 for myself, or MCVC. But you can do it whatever way you want. But essentially, we're taking a concentrated solution. So we have, let's say, 5 solute particles, and the blue are the solvent. And then we just add more solvent. So we take these 5 and then have a larger volume. The concentration's gone down. I mean, quite a lot. And so when we look at this, it's been diluted about threefold, maybe a little less, threefold. So this is a 1 to 3 dilution. 1 to 3 dilution means, whatever the initial concentration is, we'll just say molarity initial, the final molarity is going to be a 1 to 3 dilution of the initial molarity. This is the solution dilution equation. This is called the dilution factor here. In other words, if we were to do this using so we'll do molarity initial, volume initial is equal to molarity final, volume final. And so if I want the molarity final is going to equal the volume initial over the volume final times the molarity initial. And this is the dilution factor here. The dilution factor is we started off with 1 part initial, and we ended up with about 3 parts final. So I'm just guesstimating here. It's about a 1 to 3 dilution. So we expect the concentration to be about 1/3 of the original. here we're doing a solution dilution. We're going to take 100 milliliters of 0.100 molar. And so this is the 100 milliliters of 0.1 molar. And then we're going to dilute it to 1,000 milliliters. And so the final concentration here is it's a 100 to 1,000 dilution of the initial. The initial molarity is 0.100 molar. So this is going to be a 100 to 1,000 dilution of 0.100 molar. And so this is going to be a 1 to 10 dilution. So this is going to be 0.0100 molar at the end. And so that's what they have here, 0.0100. And so we look at the initial volume and the final volume, V initial and V final. And the way this is typically done is by using volumetric glassware like this. And volumetric glassware just has one mark. This is 100 milliliter. It's all been calibrated. This is 1,000 milliliter mark here. And so we pour the solute in here. And then here we got to make sure we transfer all the solute. So they're rinsing it, any residual solute in this 100 milliliter flask, all into the 1,000 milliliter flask. And then they fill this with water to hit the mark here. You know, they don't add a specific volume. They just keep filling this, and this is the most accurate way to do this until they hit the mark, which is they get the meniscus right on the line. There's a line etched into the glass here. You know, these are expensive because each one has to be calibrated, and they're all different. When you blow glass flasks like this, they aren't all identical clones. You know, there are differences in them. So the marking, this is why they have such a long neck. You know, they have a long neck here because sometimes it's down here, sometimes the marking is way up here. You know, it's a long neck can compensate for that. The long neck also means it's hard to mix. So usually we mix it thoroughly at the 2/3 mark. You know, 2/3 here, it's easy to swirl. Once you fill it all the way to the neck, it's hard to swirl that. And so what some people do is they stopper it and then flip it upside down a bunch of times. This one over here has what we call a ground glass stopper. And so this is a tight fit. This one, there's no ground glass here. You just use a rubber stopper or something to stop it there. And so here, this one, how many milliliters? So this is a little different problem. How many milliliters of commercial hydrochloric acid? Okay, so we buy the commercial stuff because it's the most concentrated. And so it's 11.6 molar. And the volume initial is the question mark here, because this is the final volume, what we want, and this is the final concentration, which we want here. And so if we want the V initial, we'll just solve for that. And so V initial is the concentrated stuff. And so that's going to be the molarity final over the molarity initial times V of the final. And so here, the final molarity is 0.500. And the initial molarity is 11.6. The molarity cancel. And the V final is 5.50 liters. And so doing this, we get 0.237 liters, which is going to be 237 milliliters. So what we do is we take 237 milliliters of the concentrated stuff and then add enough water to make 5.5 liters. And that's going to give you the 0.500 molar liters. And so here are the steps to doing it. I'm going to skip those steps and go on to stoichiometry here. This is solution stoichiometry. We've already done some solution stoichiometry. The only thing is we use molarity as a conversion factor. Molarity is an extremely useful conversion factor in solution stoichiometry. So here we have the volume and solution molarity. Okay, and then we can use the molarity to calculate the moles. Also, if we have the mole as a product, if we have the volume and solution molarity of the product, we can go the other way. And this is just inverting the molarity here. That is flipping the ratio upside down. And so let's take a look at a solution stoichiometry problem here. Calculate the volume in milliliters of 0.842 molar sodium hydroxide required to precipitate as copper 2 hydroxide, all the copper ions in 30 milliliters of 0.635 molar copper 2 sulfate. And so here, sometimes it helps to draw this out visually. And so we want the milliliters of 0.842 molar sodium hydroxide. So 0.842 molar sodium hydroxide. Required to precipitate as copper 2 hydroxide, all of the copper in 30 milliliters. So we don't know how many milliliters of this. And so the question is, how many milliliters of this do we need to react with 30.0 milliliters of 0.635 molar copper 2 sulfate? And so here we know how much copper 2 sulfate. If we have the volume and the molarity, we can get the moles. And the volume we just have to convert from milliliters to liters. And so if we have the volume and the molarity, we can get the moles. And so we have the volume of copper 2 sulfate, 30.0 milliliters. Convert that to liters. They don't. They use this. I just leave it as moles per liter. So I have one more conversion factor that I use here. That is go from milliliters to liters. And then the liters cancel for the molarity. They like to do this. They like to take a lot of shortcuts. I don't like to do that necessarily. And then we get the moles of copper 2 sulfate. And then we look at the mole ratio, a 1 to 2 mole ratio here. And so 2 moles of sodium hydroxide for 1 mole. And then the sodium hydroxide, this is pure sodium hydroxide, but we're getting the sodium hydroxide from a solution. The solution is not pure, so it's 0.842 moles of pure sodium hydroxide in 1,000 milliliters of this mixture. And so we're calculating how many milliliters of mixture are required, and that's going to be 45.2 milliliters. So 45.2 milliliters of sodium hydroxide will give us the correct number of moles to precipitate out the copper ions as copper 2 hydroxide here. So this is a solution stoichiometry problem in which we use the molarity to get us to moles, so we could do our mole-to-mole conversion. We also have titrations. Burette, we talked about that. Those are very expensive, and indicators like phenolphthalein that we use for titration. So here's our titration. We're adding sodium hydroxide. And what we want to do is we want to go from colorless to colored within a half a drop, ideally. This looks kind of dark here as far as that goes. But you want something that's clearly discernible between colorless and colored. So this is titration apparatus. There's certain words. Standardize is a procedure that we use to determine determination of the concentration of the solution to be used in titration by titrating against the primary standard. A primary standard is a substance that can be weighed accurately and has high purity and of high purity that can be used for standardization. So we have primary standards. The difference between primary standard and some other standard is this weighing part, rather than measuring volume. Measuring volume is more difficult to do accurately than just weighing something on a balance. So, and then we have standardized solutions. Standardized solutions have been standardized. All right, so here, a 25 milliliter sample of electroplating solution is analyzed for sulfuric acid concentration. It takes 46.8 milliliters of the 0.661 molar sodium hydroxide to neutralize the sample. Find the molarity of the acid. And so, in order to get the molarity of the sulfuric acid, H2SO4, we need the moles of H2SO4 divided by the liters of H2SO4 solution. All right, now the liters of H2SO4 solution, is this 25 milliliters of sulfuric acid solution. So 25 milliliters of sulfuric acid is 0.025 liters. And so we can just plug that in here, 0.025. It's 3 sig figs, liters sulfuric acid solution. So all we need is the moles of sulfuric acid. Well, the moles of sulfuric acid, we're just going to get that from stoichiometry. And so we want moles of sulfuric acid, but we have volume and molarity of sodium hydroxide. Well, if we have the volume and molarity of sodium hydroxide, then we can have the moles of sodium hydroxide. From the moles of sodium hydroxide, it's a 2-to-1 mole ratio here. And so we'll just start off with this 46.8 milliliters of sodium hydroxide solution here. And then we'll convert it to liters. So liters, 1,000 milliliters. And then we'll use the molarity, 0.661 moles of pure sodium hydroxide per liter of this mixture or solution. And then it's a 1 mole of sulfuric acid for every 2 moles of sodium hydroxide. And all the units cancel except moles of sulfuric acid. So once we calculate the moles of sulfuric acid, then we just divide that by 0.025. And that should give us the molarity of the sulfuric acid in the electroplating solution. So once we get the moles of sulfuric acid, then we divide that by 0.025. And so here they just did the conversion here. And then we get the molarity of the sulfuric acid. So that's a titration problem. Titration we're usually using or trying to solve for an unknown molarity. And so once we do this titration, then we say the sulfuric acid has been standardized, or at least if we're going to use this further for anything. Sometimes we don't say that, we just determine the concentration. All right, titration using normality, forget it. We're not going to do that. A lot of people who do a lot of titrations might prefer normality. So we're not going to be dealing with normality. However, we will be dealing with colligative properties. Colligative just means a collection of properties that kind of depend on the same thing. And the same thing is what happens when you dissolve a solute in a liquid, like water. What happens to the properties of water when there's solute dissolved in there? And what happens is some of the properties change. For example, the freezing and the boiling point change for water. And so pure water, under normal conditions, has a freezing point of 0 degrees C and a boiling point of 100 degrees C by definition. However, when we dissolve something in that, and so this is an aqueous solution of water plus whatever, the freezing point is actually less than 0 degrees C, and the boiling point is actually greater than 100 degrees C, and it depends on the concentration of solute particles. It has to be particles. Some solutes break apart into multiple particles, and so we're looking at how many particles are dissolved in there. And so freezing point, we call this, the freezing point we call a depression because the freezing point's going down. And the boiling point we call elevation. And so this is a depression, and this is an elevation. The boiling point's going up. And so freezing point depression, boiling point elevation. And that's because of what the solute particles do in interfering with the normal interactions between water molecules themselves. We have one more colligative property, and that's the vapor pressure. What happens with the vapor pressure of the water is the vapor pressure of the water goes down. And so there's a lower vapor pressure. What other colligative? Let me make sure. There's another colligative property. And so the freezing point depression, boiling point elevation, this vapor pressure lowering, and there's osmotic pressure. as well, but I don't think we're going to get into this. So this one, I think you can forget. But let's take a look at these two. I think these two are the only two we're going to concentrate on. And so colligative is a collection of properties, which would be freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure lowering as well. But out of those, we'll just look at these two. I'm pretty sure that's it. And so this is freezing point depression. Freezing point depression is given by this, depression. How much lower is it going to be? So this is the change in the freezing point here, delta T. This is change in freezing point. And that's going to be proportional to the molality of all the particles. Let's see where that goes. And this is the freezing point depression constant, Kf, and that depends on the solvent. Solvent Kf. So it's water. It's like one. Let's see, what was it? 1.8 roughly for water. I'll tell you the length heat. It's 1.86, I think it was, degrees per mole. And for boiling point, we have another one. Okay, so freezing point, when we have these solute like this dye here, it's interfering with the ice formation, nucleation of ice crystals. So that's one way of thinking about it. And so the solute screws up or interferes with normal ice formation. Therefore, it's going to require lower and lower temperatures depending on how concentrated this is. The more concentrated this is, the lower the temperature that's required. We could do this quantitatively here. This is a freezing point solution of urea in water. And so what we have to do is we have to get the molality. And so this is 12 grams solute, 250 grams of solvent. Calculate the molality, it's moles, so they just do a gram to mole conversion here, divided by kilograms of solvent. And so we convert from grams to kilograms here of the pure water, and we get 0.800 mole out. Once we get 0.100 mole out, the freezing point depression constant is 1.86 degrees C per mole out. So for every mole out of particles, that's going to do. Now we have to look, is this strong electrolyte, weak electrolyte, or non-electrolyte? It turns out this is non-electrolyte, and so we don't have to, this doesn't break apart into more particles, it just stays as one particle. And so that's it. And so we just calculate the change in the freezing point. It's 1.49. It's a depression. And so we take our normal freezing point and depress it by minus 1.49, and we get minus 1.49. And so this negative comes in here because it's a depression. And we have to know that the freezing point is going to be depressed. It's going to be depressed by 1.49 degrees C in this case. We also have boiling point, which goes the opposite way. It's boiling point elevation. And so we have it very similar. The change in the boiling point is directly proportional to the molality, how many particles it solves. And we can calculate this quantitatively by looking at Kb. For water, Kb is like 0.5, 0.5 something. Take a look at it. You don't have to have those numbers memorized. And so the first thing is we need the molality. And so this is where we use molality. Actually, the molar boiling point elevation constant of benzene is 2.5 degrees. So this is the Kb, the constant, 2.5 degrees C for every mole. A solution of 15.2 grams of unknown solute and 91.1 grams of benzene boils at a temperature of 2.1 degrees C higher than the boiling point of pure benzene. Estimate the molar mass of the solute. Okay, so this is a little bit different because they tell us the change and they tell us Kb, and so this is our unknown here. So we can solve for our unknown and we get 0.84 mole out. And then they tell us how many grams that we have. and 91.1 grams of benzene. And so this is not an aqueous solution. So here it's going to be moles. Molal is going to be moles of benzene. Not moles of solute, sorry. Moles of solute per kilogram of benzene. So that we have 91.1 grams of benzene, and we convert that to kilograms. Since we have the molality, this was given, then we can use molality as a conversion factor to get the moles of solute. So once we get the moles of solute here, then we can figure out the molar mass. The molar mass is grams of solute, so they give us this. This is given as well. 15.2 grams of solute. And then we calculated the moles here, so we get the grams per mole. And that gives us about 200 grams per mole of the solute. And so one application of boiling point elevation is determining unknown molar masses. All right, so what this last example illustrates is an application of boiling point elevation. The application of boiling point elevation is to determine an unknown molar mass. And if you determine an unknown molar mass, then that's a step in determining what the identity of the unknown is. And so this is an interesting example, this last one. The other colligative properties, that is vapor pressure, lowering, and osmotic pressure, aren't discussed here, but they are discussed in Chem 1A. And so that pretty much concludes chapter 16 here. There's also chapter 17, which is the next one, and that deals with acid-base or proton transfer reactions. And so one thing I wanted to talk about here, we can take a look at. It's this. I'll make this in the next video here. So I'm going to stop this video here.